Thank you so much for coming out. I'm really glad to be here for another year, and this time talking about large language models. Let's get right into it. My name is Bill Dimmer-Kuppa, and I work for the Microsoft Security Response Center, leading emerging threats. I have a low-level background in software security, but I also do cloud security. I've experimented with large language models for a little over a year, but one disclaimer I want to start with is that I'm not a machine learning expert. I don't have the academic background. I'm going to show you how I applied large language models, but most of this talk is still going to remain on my opinions rather than demonstrated academic research. So what is this talk going to be about? Well, number one, I'm going to tell you about large language models and their advantages. I'm going to tell you why MSRC is interested in them, how we've been able to apply it for one part of our security response, what are they capable of, and what's our take on their future, and also how you can get the right data to use them effectively. Now, what this talk isn't going to be about is the top 5 mind-bending ways you can use LLMs. This isn't a formal literature review or a deep dive into neural networks. And this is certainly not a representation of all AI research in Microsoft or even MSRC alone. We're a massive company, and this is a small part of our work into leveraging machine learning for our security use cases. And finally, I'm not here to sell you on Microsoft products. That's not my job. I'm going to show you what I was able to do and what I found worked, but I'm not going to sell Azure OpenAI or our commercial offerings in this talk at all. No product pitches. So for some background, the Microsoft Security Response Center handles every vulnerability reported to Microsoft. We have a massive scope. This includes all software and web applications you can think of when Microsoft pops into mind. Now, over the years, especially since 2016, we've noticed that our case volume has increased by nearly a tenfold. This graph represents the CVEs by year, and it's available through our public MSRC API. As you can see from 2016, where we used to have roughly 200 to 400 annual cases that met the bar for a CVE, now we deal with nearly 1,000 every year. And this presents an interesting challenge. How can we tackle this large increase in volume besides just adding more resources to the problem? That's always going to be the easy solution. So the reason why we were interested in large language models is because there's a surplus of security-related data. And now there is a challenge of collecting it. For example, internally, we obviously have access to Microsoft vulnerability data and our analysis and patches, et cetera. But externally, there's CVE databases, open source vulnerability data. There's a lot of it, like exploits and analysis available publicly, and et cetera. And what we noticed was that we have a lot of repetitive response workflows. And even if they're technically demanding, they're still very repetitive. And many don't require perfection. So this is why we were interested in seeing whether large language models could do anything for these security response workflows. So some background. Now, what are large language models on a fundamental level? Well, from a high level, they're statistical models designed to understand, and that's in air quotes, and generate natural language. They represent text using tokens. So, for example, given a sentence, let's go to NY, it breaks it down into different characters and subsets of the sentence based on what's called a tokenizer. And the tokenization is the process of splitting this text into fragments known as tokens. So tokens usually represent different meanings in the English language or whatever language the model is trained on. For example, the explanation point might be its own token because that has a different meaning than all the other words and all the other symbols. And the really interesting part about this is these tokens are fed into the large language model to generate a vector of floats, and this vector is known as embeddings. Embeddings represent tokens in a way that has meaning for the large language model. For example, on the image on the right, you can see dog is converted into the 0.6, 0.9, 0.1, 0.4 floats. And you do that for each different word. And once you convert that into an embedding, you can now compare different words by their semantic meaning. You know, in the right example, you can see that king and queen are quite close to each other when you graph it. And that's the really interesting part about large language models, is that it represents semantic meaning through numbers. And numbers we can do a lot of different math with. So from a high level, there's two basic building blocks we're going to be focusing on that LLMs provide. Number one is chat completions. This can be thought of as ChatGPT, but over an API. You know, chat completions works by providing a conversation. For example, first a system prompt specifies what the large language model is supposed to do. You are a helpful assistant. Then you can provide a user question like, who won the World Series? And you can also provide a conversation that's already had answered questions as context. And the chat completions API allows us to generate the next message in the conversation. So for example, when the user asks, where was it played? Well, the assistant then generates, the 2020 World Series was played in Texas at Globe Life Field in Arlington. Now, the second fundamental building block we'll be talking about is called fine-tuning. So models can learn from your use case from a set of input and output examples. The cool part about this is that, unlike the chat completions API, you don't actually need to provide a lot of instructions. What you instead provide is a lot of sets of chat completions, like conversations, that represent what the assistant is supposed to output in the first place. And with enough of that data, the model can actually learn the instructions based on the examples alone. Instead of prompt quality, so that's the instruction quality for the chat completions API, input quality, the examples you have is what counts. Now, fine-tuning is going to be best when you have enough of the right data. Performance depends on the nuance that is hard to represent in a prompt. So, you know, for some security response use cases, we've seen a lot of different details that can really change the output, which is hard to express in a small set of instructions. And fine-tuning is also really useful when you want a specific output format or a tone of your message. Now, the greatest value LLMs provide, in my opinion, is that it gives you the ability to interface with any data you can represent with natural language. And the cool part is, most data can be represented as natural language because that's just words. Humans use words to communicate. So LLMs reduce the barrier for deriving value from most data. So one of the early examples I tried out last year was related to the Microsoft Security Response Center Security Update Guide. Every Patch Tuesday, we release CVEs on the Security Update Guide, and every CVE gets its own page. These pages include basic metadata like the name of the vulnerability, the impact category, the CWE. It also includes FAQ questions, so a set of questions that a customer might want to ask about a specific CVE. But what happened was, as our volume increased, the data we shared through the Security Update Guide actually decreased. It became really hard to have the same level of time for each CVE when our volume was increased by tenfold over the past 10 years. So I was kind of curious, can we actually generate some of this extra data that we used to provide using large language models? So this is a pretty simple example, but I want to go through it because it helps us understand what using large language models looks like in practice. The first thing I did was grab training data. So remember the additional context we used to provide? I was able to scrape that data using our public API and got every single FAQ entry, all CVSS scores, and also executive summaries for older cases that had one. You can see a snippet of the code I used on the right. It was really as simple as parsing the JSON provided by the server. And for some extra data, I also parsed our internal analysis notes and metadata that we had about the case using our internal documented API. And the really important part here is that getting the right data can really help make your model a lot more effective in the use case you're trying to go after. Let's separate this use case into challenges and develop a strategy around it. So number one, the first thing we used to provide is executive summaries. How can we leverage the set of summaries we used to provide in order to generate new ones for new cases? Now, we first chose fine-tuning for this. And an alternative approach would include using chat completions, but what we really wanted to focus on was maintaining the tone and consistency that we used to have in our old FAQs and executive summaries. So, for example, with chat completions, you could do something called a few-shot prompt. And that involves taking a set of examples, maybe 3 to 4, and then providing it in the instructions so the model knows what the output format should look like. And another example would be something called a retrieval augmented generation approach. So in this case, you would provide examples that are most relevant to the case at hand. You'd find in 2016, maybe there was a vulnerability very similar to this one. And you'd find that case, you'd find that executive summary, and provide that example, which can help increase the output quality. So from a high level, our strategy was split into pre-training and post-training. Number one, we would scrape all the summaries from 2015 to 2021. We'd then fine-tune GPT 3.5 based on a partial executive summary. And then after we had that summary generated through fine-tuning, we'd use the model to generate 10 summaries. We'd then pass it to GPT-4 to fix hallucinations and grammatical errors. And we'd also add a redact layer where we redact sensitive information with a GPT-4 prompt. Now, the key thing to understand here is, number one, you don't want to do everything in one single step. You want to split your task into very fundamental levels. So in this case, it includes first to generate 10 summaries that we want to include in a summarization model. And once we have those 10 summaries, we summarize those using GPT-4. And in this case, it's really as simple as, summarize these 10 summaries together, create a summary of the summary, you can say. And once you have the summary of the summary, you can finally add an extra layer to make sure there's no sensitive data from our internal analysis notes that are included. So for preparing the data for fine-tuning, it's just like chat completions. So what you do is you create conversations like you would for a chat completion API, but you just create multiple examples. Now, the prompt is simple. Because we want the model to learn from our data, we just provide a sentence or two. You are an expert security engineer responsible for writing a summary for a security vulnerability. And the user message is going to be our input data, which includes the impact of the vulnerability, the CVSS vector, the root cause category, so is it an out-of-bounds write, out-of-bounds read, et cetera, and finally, the technical analysis notes from the MSRC internal team. And finally, the assistant message is going to be the output we expect. And so since we're training against these old CVEs, we'd provide a user message for that old CVE, and then we'd provide the real executive summary that we published on the security update guide. Now, we use Azure OpenAI for training, but you don't have to. All you really do is, with those conversations we just generated, we put it into a JSON lines file, where every line is a different conversation. And then you just really pass it into a AI platform like Azure OpenAI, or even OpenAI itself. And it'll automatically go through these examples and fine-tune your model based on it. And you can see a graph here where model training loss is represented in red. The lower your loss, the closer the model is to an accurate output. And generally speaking, lower loss is going to be better, because it means that the model is, at first we can see the model has no idea what it's doing. The loss is at, 4.0 nearly? And then as it's given more and more examples, it's actually able to really reduce that loss down to nearly, under 0.5. It's never going to be 100% exactly right most of the time, but it does get you pretty close to what you need. Now, the next challenge was also generating FAQ entries. We don't want to just generate a summary, but we want to generate new questions based on the analysis notes that we have. We ended up with a chain of GPT-4 prompts, and this is called an agent approach. So there's no fine-tuning, because we wanted to really focus on creativity. Now, this was the most challenging, because generating new FAQ entries that we don't have extensive data for, beyond what's already included in our assessment, is not trivial. We spent a lot of time reviewing our FAQ entries from past cases to really target and focus on the tone we were interested in. And again, from a high level, our strategy really included breaking these steps into different parts, which includes generating the questions, parsing and filtering out errors, selecting the best questions. That's another great strategy is once you generate like 10 or 15 different FAQ questions, you ask the model to pick the best ones. And then we simplify each of these question sets, and so to get rid of duplicate data as well. And finally, we'll again redact sensitive info and select the best question. Now, the prompts are too long to show, but I want to show you a little bit of a breakdown. You can see a snippet of it on the right. We start with a preamble with personality and context. So what is the model doing? What's its job? We give it examples of bad questions and why these questions shouldn't be generated in the first place. We also tell it how to format its output. This included, in my case, question on one line and then the answer on another line with a colon before. And we give it example questions that we want it to answer. These are the types of questions we'd like you to generate an FAQ entry for. And we also finally give it some guidelines in tone and style. Now, this can certainly be improved, but it was more than enough for our use case. A lot of these techniques that went into the last prompt came from actually OpenAI. They have a great blog known as the OpenAI Cookbook, where they publish different tips and tricks to really improve, for example, in this case, reliability of your model, but they have everything you can imagine of for fine-tuning as well. This came from simplifying instructions, targeting the right tone, splitting tasks into their basic steps, and asking the model to generate why it generated a specific entry to reduce hallucinations, and also generating several variations to select the best suggestions. So just to give you an example of what this project output looked like, you can see on the left, this is a real CVE that was published. The left is what we included in our FAQ. And then on the right is what the LLM was able to generate for the CVE in question. You can see that in the real CVE, we provided a single question about, the attack complexity is high, what does that mean? Whereas in the LLM-generated CVE, there is multiple questions about the attack scenario. What would a user, need to do to, what would an attacker need to do to exploit this vulnerability? And also details about whether it's network accessible, and et cetera. Now, one thing I do want to call out is that the LLM failed to derive the exact same question that we'd expect in the real CVE. There is no mention about the attack complexity being high, et cetera. Now, we didn't include these types of templated questions on purpose, but we could have considered it as a future value add. And in general, the results, what we saw was that we could first improve by generating these required template questions. Now, I want to also clarify that it wasn't perfect in the sense of there were hallucinations. There would sometimes be statements that are made that were factually false. This is not used in production. If you go onto the security update guide today, we're not using it because of some of these challenges. Another really important one was around the translations. So we support customers around the world. And if we create these custom content for each CVE, there's over 100 CVEs. How do you actually convert that into every different language? Machine translations aren't that great. And this is also why you might notice some questions on the MSRC security update guide, they look very repetitive, is because we generate these translations once, and then we can reuse those generated translations for multiple CVEs. But I did want to demonstrate this really basic example to get you introduced into fine-tuning and the chat completions API, and to show you the types of tasks that LLMs are good at. Now, another interesting use case that I found for large language models is to be able to predict key facts about a case. Can we use large language models to predict facts about an MSRC vulnerability report to help measure risk? Example is we can predict the severity and impact of a case based on its report. And ideally, we could produce a generic methodology to predict any field. And the idea behind this was that sometimes we receive reports that turn out to be like spam reports, to be honest with you. I'm not even talking about low or moderate severity vulnerabilities. I'm talking about vulnerabilities that wouldn't even be considered a vulnerability. And what we can do is we can help reduce the impact volume has on our business if we can measure what cases we should take a closer look at and prioritize. So the training strategy for this was pretty simple. We had a simple prompt because we wanted to learn from our training data. And the user message included the security project manager. And what that really means is this is the person that deals with handling your MSRC case from start to finish. So when a case is opened, they'll first do initial triage to make sure it's legitimate. Should we forward it for internal analysis? Now, number 2 is the React engineer name. And from a high level, these are the people that do the technical analysis of your vulnerability report. And we included these names for a very important reason. And finally, we have the technical analysis from the React engineer. And we also have the vertical about what is the product that's impacted here. You can see in the user message, this is where the data is represented as our input, and the output is what we want the model to generate. The reason I mentioned the name is really important to include is because it allows us to bring multiple perspectives into the training process. Maybe some project managers were better at predicting legitimate cases than others. Maybe some React engineers have a stricter interpretation of the servicing criteria. And this allows us to bring a lot more diverse perspectives. So for example, we can provide different names. After we fine-tuned the model, I can go through every person on my team and get them to think, hey, does this case meet the bar for servicing? Or does this case, should we prioritize it for immediate servicing? And less successful metadata, this is an important one too, is you don't want to just put everything you have into this training prompt. It's like researcher name and statistics, how often did they submit legitimate cases, examples of past similar cases. When we included this metadata, what we noticed was an overfit. So it would rely too much on these fields that weren't always 100% accurate. And it basically cheated off of the past examples we would give it, whereas we wanted it to learn to help predict some of these issues ahead of time without needing that initial example data. We trained on nearly 6,640 of these cases, and we had a loss mean of 0.26, which is fairly good, and we had a standard deviation of 0.55. The minimum loss came down to 0.01, and what that represents is sometimes the model was really, really good at predicting the outcome of a case before an analysis was even created. So for the results of this, we had a roughly, initially, 61% accuracy for exact severity. So that's low, moderate, important, critical. We had a 63% accuracy for exact resolution. So that's fix the next version, no repro, won't fix, fix in security update, et cetera. Now, the issue with the low accuracy counts is that there's a lot of variance between the important, moderate, critical, low vulnerability ratings. And what really mattered is whether we fix an issue in a security update. And what that means is, do we prioritize this report for immediate servicing? Because those reports are the ones we'd like to prioritize the highest. And the other issues are still important, but they don't necessarily meet the bar for immediate prioritization. And once we actually filtered for this general category of fix and security update, we were able to get it up to 75 to 82% accuracy. And the reason this is really interesting is, keep in mind, this is before any analysis is actually done of the vulnerability besides the report being sent into MSRC. So we're able to get ahead of the case, make sure to understand which ones are going to be the most important and which ones are going to need that less prioritization, et cetera. And the really cool part about this is it was really simple. All we did was provided the input, like report and output outcome of the case. And the large language models allowed us to derive value from that data without actually needing to do much at all. Like, again, all we had to do was provide those examples, and it was able to find those patterns. It's just like traditional machine learning. We could have used a very simple logarithmic regression model to probably get an outcome like this as well. But the key here is just, again, how simple large language models make it. It's not necessarily going to be as performant as some of these other approaches, but they're a lot faster to implement in practice. And this generic methodology also worked a lot in a lot of different cases, not just this one. Now, one thing I do want to call out about this example is going to be prompt injection. Unlike the last use case, we actually included an untrusted finder report for input. And this exposes us to potential prompt injection attacks. What do we do about that? Well, you want to try to solve it by design rather than detection. If you're dealing with untrusted data, make the impact not matter at all. So for example, could a researcher include some weird instruction in their report to make it ignore all your instructions and instead output this specific data instead. They could, but the point there is if they can do that, make sure the impact is limited. In this case, there's always humans involved in the loop. The worst case you can ever do is maybe make a case seem riskier than reality. And in the end of the day, if you solve it by design, you have to worry a lot less about things like, can an attacker inject something into our model, because it just won't matter at the end of the day. All right, this is a really interesting example I want to talk to you about. So far we focused on summarization and classification, but large language models, one of their really big value adds is going to be the universal interface aspect. I was curious whether they could also help solve these hard technical problems that really require a lot of expertise and a lot of not necessarily decades, but several years of experience. So I was curious, could large language models generate a root cause summary of a vulnerability based on a crash dump alone? Now, finding the root cause category of a vulnerability based on a crash dump is not new. If you've ever dealt with a crash dump, of a vulnerability, or in general any crash dump, WinDebug, the tool you can use to interact with these dumps, actually has a little bit of analysis built into it. So for example, in this case, if you type analyze-v on a crash dump, that's a command you're going to use, it'll tell you it's a page fault in a non-page area in this case, and it gives you like the faulting source code, etc. But what we're talking about is not actually a root cause category, but a root cause summary. I'm interested, can it actually explain what's happening here with the vulnerability? Far more than what type of crash occurred, out of bounds write, whatever it is, and where it occurred. And this hasn't really been done before. I've seen a lot of approaches with code, but they've really failed because of the diversity of input with crash dumps. Now, many vulnerabilities lead to a crash generating a dump file, and dump files can contain a lot of useful information about what's going on with this case. One of the most common artifacts we see through reproducing a vulnerability report are these crash dumps. And the cool part is it works for user mode and kernel mode vulnerabilities. There are some newer technologies like time travel traces, which help you record everything that's happening in the process when a certain exception occurs. But unlike that, we actually now have support for user mode and kernel mode. Time travel is limited to user mode. And these crashes can contain information like where did the crash occur, what were the variables when the crash triggered, and what's the story behind the function that led up to the crash. And the dumps can also help us automatically find source information, the stack, the registers, all this useful data that occurred at the point of the vulnerability being triggered. Now, the key challenge in this case was really converting a crash dump into natural language. So remember how we had the chat completions? We need to now convert from a crash dump into something, just words, to be honest. We tried to use only a few examples, but if you've analyzed crash dumps, you understand the complexity that goes into analyzing root causes. And that's why we really needed a lot more crash dumps in the first place, and that's why we focused on getting a lot of crash dump material. So how do we actually go from dumps to natural language? Well, WinDebug has a console variant known as CDB, which is the console debugger. And it allows us to really interact with crash dumps on a programmatic level instead of the UI WinDebug that a lot of you are probably familiar with. So in this case, I used a wrapper for this console debugger known as CDB in PyCDB. And it allowed me to interact with crash dumps from Python, which really made it simple to get the data I needed from the crash dumps and into a prompt that I could provide for fine-tuning. So I basically wrote a wrapper for a wrapper in this case. I automatically extracted key information like the call stack, the local variables, the analyze command, and it really was just using regex and WinDebug commands. You can see the different functions I implemented on the right, but it wasn't anything too fancy. I would just run a command and then use regex to output the parts that I needed, to capture the parts that I needed. And this really helped me convert the crash dumps into a form that I could represent in normal text. Now, another big challenge for crash dumps was getting into the source code. Decompilation might work, but source code is going to help us provide that context around what's happening in the function at a level that decompilation isn't going to be able to provide. Now, if you're doing just for small projects, you can use source from disk, but I don't have every Microsoft product cloned to my cloned to my machine. And proper access controls, at least in Microsoft, really make this harder than you expect. So for this approach, I first started with an agent model. So just using simple instructions to see if I can get a response that I was interested in. This included, what is the function used for? What are the local variables? Can you summarize the flow of this function? What variable is responsible for the crash? Why did a variable trigger the crash in the first place? And then slowly, we'd build this repository of information about a crash dump all the way to generating a concise report about the root cause of a vulnerability. But unfortunately, with the agent approach, it really didn't have that great results. Even for simple vulnerabilities, I mean, you got sometimes a generally rough idea of what was going on, but again, it really had a trouble capturing the nuance that went into analyzing these crash dumps. And it's definitely struggled with use after freeze and race conditions. And sometimes it was partially correct, but it missed the whole story. This is why we went into fine-tuning, because if we could get the sample data, we could get the model to learn off of that data instead of in our instructions alone. So the dump analysis work had by far the most strategies out of any project I've worked on with large language models. It's not as simple as point and shoot to get good results. In general, I use GPT-4 to generate a root cause summary based on our existing analysis notes. That's to get our assistant message output. But besides that, for the input data, it was a lot more complicated, again, a lot more complicated than you could expect. You can read this offline once I release slides, but from a high level, I want to show you the type of iteration and experimentation that goes into this work. So instead of, there's not going to be a perfect solution for every use case. You want to start with the best guess and then iterate off of that to see what works. So first, I tried with GPT 3.5, can we just fit as many crash frames into the input as possible, and that started with a loss average of 1.4. That's very high, and it wasn't accurate at all. Now, I optimized some automation to use some of the dumps that were seemed unviable, and I removed low-quality cases from the training set. And you can see, as I iterated and I iterated on these different strategies, I slowly chipped away at that average loss. I started at 1.4, but by slowly, again, changing the strategy of the input data, I was able to slowly get it down to 0.87. And again, the point here is there's not going to be a perfect solution for your use case. You really have to experiment and see what works. And the final strategies was also an improvement in the fundamental model that I was using to train with. So in 2024, Azure OpenAI increased the fine-tuning context window. So that's how much input you can provide in the input for your fine-tuned model to 16,000 instead of 4,000. And this helped a lot with the challenge of too many relevant stack frames and not enough space to fit them in. I removed dumps to help really remove inconsistency from my training data. And then finally, in late 2024 or mid-2024, Azure OpenAI and OpenAI introduced GPT-4 fine-tuning. And what I was able to see is just by changing the fundamental model I was training with, or foundational model, I was able to have a 16% decrease in my loss. So to recap, I started with a mean of 1.41 for my training loss, and I ended up with a 0.42, a nearly 70% increase, or a decrease, excuse me. And this really shows the value in that iterative experimentation work, but I want to show you what this model really looks like in practice. So in this report, we have a legitimate vulnerability from a researcher where the wallet service had an integer overflow. It would increment a reference counter, and that was accessible over COM. And if you just called this function over and over and over again, there would be an overflow. The real root cause summary for this vulnerability was due to a reference counter only being 32 bits. It's possible to overflow the reference count, leading to a use after free. And when the LLM model generated one, here's what it had to say. The root cause of the vulnerability is a reference count overflow in the walletX object, which leads to a use after free. Now, what was really interesting to me is that I was actually able to capture the key pieces of the vulnerability in a way that we've never seen before for dump analysis tools. In this case, it found the same m_cref variable that overflowed with the function addRef. it was able to see that it bypassed a condition inside of the release function that checks if the reference counter is not 0. And this led to the execution of a delete, which led to the use after free in the first place. Again, I just want to highlight, this is all from a crash dump. There's no cheating. It doesn't have the final report in this case. It all came from the crash dump alone. And this is something that would usually take years for an individual engineer to learn how to do properly. Another example was, in this case, the UX init DLL was loading an untrusted file from disk, and it had a specific part of that file that it didn't do enough validation on. In this case, it was the file path of the theme that was included in the file. The offset of this file, et cetera, was controlled by an attacker, and the function failed to do validation whether this was legitimate at all. Again, the real root cause summary expanded on how this assumption that the size is at least max path, but the buffer that was copying this path into didn't actually need to necessarily have. You could copy more than max path because of a lack of a validation check into the input file. And with the large language model, we were able to see, again, it captured the right key facts about the root cause based on the dump analysis alone. It found that the DLL name, which points to a location in the untrusted file, was not validated, and it assumed the size of the destination buffer to be max path, but since the offset is never checked, that's not always the case, and this can lead to an out-of-bounds write. The dump analysis work wasn't perfect. There were still cases where the right context wasn't available, like in race conditions and use after freeze. It struggled a lot with that. But it also highlighted the interesting part that what large language models are capable of today. If you can get it the right context, it can do really hard technical problems for you. And especially if the technical problem doesn't need that much precision, that's even better for the output. And here you have a list of things I'd like to do better over time, especially as we get more data and we improve our input to get the RCA correct. So just to summarize the lessons for your organization, number one is data is above all. You don't necessarily need examples for using large language models, but it can greatly improve your chance of success. You need to really have a hacker mindset here. If you can see the data, you can scrape it. And that's the model I use in my head is, like, if I saw source code, I can see it with my web browser, then I can scrape that source code as well. Now, MSRC uses internal data, but there's a lot of external equivalents, like the open source vulnerability data I mentioned. The Linux kernel is a really great example of that. They have a lot of fixed vulnerabilities, with including patches and the issue's original description. Look for ways to generate the data from what you already have. For dumps, there wasn't an easy solution at all. I just begged my team to give me crash dumps, and eventually I was able to get nearly 500 that were viable for training. But in reality, it's going to be a lot more complicated than this, especially if you're dealing with external data. You can use the large language model's universal interface advantage in order to convert the data you can get into data you need. And so, yeah, the real big principles we want to keep in mind is derive the data you need from what you have. So, for example, with the root cause summary work, I first generated a root cause summary based on internal analysis notes. You want to normalize your input data to make it uniform. Don't be afraid to get your hands dirty, and really leverage the fact that LLMs allow you to interact with nearly all data you can represent in words. Now, what makes a problem a good fit? It's going to be data diversity. Do you have enough data for your problem? And is it easy to solve your problem with code? Because if it isn't, like the crash dump analysis work, then the more value large language models have to offer. Is there room for imperfection in a solution? Can you break down your problem into logical steps, or do you have enough data to fine-tune a model to learn for you? So if you want to apply large language models to your work, find what makes your life hard, find what you have a lot of data for, and really just try. Experiment is the biggest advice I can give you. There's no perfect solution for every use case. It might work, it might not work. I was able to show you a few capabilities today that did work for me, but it's really up to you to apply that to your business and for your use cases. I'd also be really careful with large language models. There's a lot of hype right now going around them. I do think that they provide some value, but nowhere near as much as some people believe. I think that they're above average in terms of their potential value, but whenever someone's telling you about AI and how they're leveraging it, really make sure to understand their incentives. Do they make a living off of thought leadership? Do they work for a company that's going to sell you more AI products? I'd be really careful with considering the output of work you see online, especially with malformed incentives, to align with what you know works until you reproduce it yourself. I wouldn't underestimate traditional machine learning. If this is what we can do with models today, think about what we can do with models tomorrow. And the final piece of advice I'd give you is start collecting data now. Thank you so much for coming out to my talk.